Have a good panel ahead to kick things off this morning, and looking forward to that. Going to be some good conversation. Lots going on in the climate change and carbon pricing space. Lots of interesting considerations, especially for remote and northern regions. Before we get to the panel, however, we have a presentation on a joint case study entitled Exploring Fuel Options for a Remote and Northern Mine. So to deliver that, I'd like to call to the stage Nicholas Allen and Danielle Séguin. Come on up, guys.
So, good morning, everyone. My name is Nicholas Allen. I work for BBA, a power engineer. For those who don't know BBA, we are a consultant engineering firm. Actually, for the last 40 years, we've been working in energy, in power, mining metals, oil, gas, biofuels. So, we actually have offices right now all across Canada, so from Vancouver to Labrador City, and have offices here in Toronto. Myself, I've been working in off-grid power plants for the last 10 years. So I've designed, I've optimized, I've troubleshooted a lot of the power plants in northern Canada, in the Arctic, also in the hotter African countries. So this is my experience. Maybe I'll present also our client, Danielle Séguin.
So good morning, everyone. My name is Danielle Séguin. I'm working with Agnico Eagle. I've been with the Agnico project team for 10 years now. Our team is basically going where's their major project for Agnico, for the company. So we've worked in different locations, Mexico, Finland, Abitibi region, of course, but also the Nunavut for the most recent year. Maybe a couple words on Agnico Eagle. So 9 gold mine in production. Different hub, so again, Mexico, Finland, Abitibi, and we're working a lot right now on the Nunavut hub, so developing this region of the world. So, move forward. What it means to build a mine in Nunavut. Of course, we're off-grid. What it means when CAPEX, schedule, IRR are all major player in the equation. What we did at Agnico, we've studied, and we've studied a lot. It was sometimes painful, if I could say. We've took the project, we've reversed it all over, but at the end, we have a project that is moving forward today. So most of our study that we did was the standard power plant, diesel, engine, fuel. But when we went out for bid, we knew that LNG was close. It was somewhere in the cloud or whatever. We knew it was there. I don't know how it works, but it was there. So we've decided to keep an option open with our bids to ask for a machine that could be converted to LNG. So when we've received the bid, we've realized that it was approximately 1% more CAPEX to go with an engine that could be converted to LNG in the future. So basically, we've decided to do not paint ourselves in the corner. And thanks, Nick, for the nice picture. I know it took you the whole weekend to do that, but that's good.
That's good.
Next slide, please.
So, we start?
We'll start.
All right. So before, we'll go more to the details, but before, or maybe you want to talk to the
Yeah, I'll do a small wrap-up. So, a bit more on the Meliadine project. There's a lot of interest around this project. So, as I mentioned, it took 7 years to develop this project since we've purchased it. We've received our board approval in February this year. One important thing to mention is that when we've received the approval, we were at 60% of detailed engineering complete. So we knew the project, we had a lot of information on it, and it was well detailed. We split the engineering with 3 consultants. It's a major project, so we had to split the pie a bit. So BBA, Nick and his team had everything related to energy. So power plant design, electrical distribution, heat recovery system, it was all BBA. The status of the project at this stage right now, we're more than 90% completed on the engineering. we've had one major goal this year, and it was to close our 3 main buildings, because in Nunavut, the weather, it's never easy. So we wanted to close our, what we call our multi-service building, where the warehouse, garage going to be. We wanted to close our process plant and also our power plant. So this objective is done. There's still a challenge to come, so we'll start now with the mechanical, piping, electrical, and instrumentation installation early next year. So there's still some challenge, but right now we're exactly where we wanted to be with the development of the project. So next slide, please. Okay, so more specifically on the power plant now. I think the numbers here speak for themselves. The power plant is 12% of the infrastructure capex that we have on the project. The OpEx, it's 14%. More importantly, the power plant will consume 75% of the fuel that we will use around the life of mine. So therefore, the energy is definitely a top strategic item for Agnico, and we have to pay a special attention to it, especially at the design stage. So next portion of the presentation, I'll let Nick explain to you the technical stuff, because he's way more brilliant than me to do it. So
Thanks,
Nick,
Daniel.
there you go.
All right. So we were going to talk about the different options that were available for us for power generation. Before I go into these options, just want to talk about the challenges that we have in design for Arctic regions like Meliadine. We are so remote that reliability is really always our #1 priority. So whatever else is talked about, this will drive most of our decisions. Electrical loads, high variations, quick variations, that's due to the fact that we have a relatively small network and large equipment in there, so like ball mill motors. So network stability is always very critical and has to be considered again in all the choices we'll make. What's interesting is a site like Meliadine, the heating load is actually sometimes higher than the electrical load. So we tend on focusing on the electrical load, but thermal is as important for a site like Meliadine. So for heating the buildings, but also heating the ventilation air for the mine. Delivery period, so because of the ice, we actually only have 4 months for which we can deliver by sea, and that's when everything goes well. So you can imagine that the storage capacity for parts, for fuel, is quite big. The actual fuel, no surprise, it's quite expensive. The logistics are quite complex, so we actually get the fuel all around Quebec by sea, then across the Hudson Bay into Rankin Inlet, then again transferred into trucks into Meliadine. So it's a pretty large logistics of transportation to get the fuel up there. Maybe I'll just finish on the Arctic conditions. So very cold. We have a lot of blizzards. There's a permafrost. So again, all these things are things that we have to consider when we're designing the power plant in the Arctic and in Meliadine. Technology was actually chosen in one of those studies that Daniel was talking about, so the conceptual part of the project. And we really evaluated all options. The most standard being the gensets, the turbines, which can be interesting, hydro, renewables like solar and wind. But in the end, we came back to the genset just because of the following reasons. The reliability that we have with these engines, they're very robust, makes a very good choice. Also manpower, you got to think about manpower in the north like this. The technical resources are easily available for gensets. Electrical efficiency is getting always better, and we're getting more than 45% efficiency electrically out of these engines, so it is, again, interesting. Load pickup capabilities, so these engines can quickly react to the variations in loads, so grid stability is quite good with this type of technology. And also heat recovery, I'd like to say, since we want to recover all the heat that we want, and it's pretty simple to recover the heat from these engines. So we just have water glycol networks. We don't have to have steam networks that require more maintenance or are more complicated. So now, what we've been talking a lot about, renewables. In our case, in a project like this, where CapEx is really minimized at year 0, and it's a type of project that just builds up, so every year it's going to get bigger, even in terms of throughput, it's the same with energy. So we start with a standard option, and solar and wind will just be something that will be integrated later during the project. But at year 0, it was the standard genset option that was kept. Yes, thermal load. So like I was saying, thermal load quite important. What we try to do is to have centralized heating networks. So the more centralized network we have, the more possibilities we have. All the heat recovery from the power plant we can inject into this network, but also just having efficient equipment like boilers on this equipment. On this network, or even recovering heat from any other equipment can be thrown into this network. So that's what we have done. We try to avoid having decentralized burners, or I would say avoid even more having electrical heating. That's a no-go because heating electrically is half as efficient as heating with just a diesel boiler. So that's technology. So we chose the genset. In terms of fuel, again, there are many options. Even though we are remote, we are cold. The standard is the Arctic diesel, so diesel that can, well, the cloud points at minus 42 degrees Celsius. But for a site, even like Meliadine, you can use regular diesel, or summer grade diesel. So that's another option that we kept in mind, biodiesel also. And finally, natural gas is something interesting for the north. There's more and more opportunities, and it's in the liquefied form, so all the other forms are not necessarily interesting. And I won't go through propane or heavy fuel oil because it's so remote, so cold that it's definitely not an option. Maybe I'll start with my beautiful picture of being painted in the corner, but just to say that that standard option, the genset with Arctic diesel, standard, typical option, which is safe, which works, what does that represent for a site like Meliadine? Electrical load will vary a bit, but we're expecting an average load of 20 megawatts. And for 20 megawatts, for this type of standard option, we're expecting 40 million liters of fuel consumption every year. And that in turn produces about 110,000 tons of greenhouse gases every year. So that's the standard options. We've done studies, we've talked about it a lot, and we're trying to see what else is possible for this site, even though it's rough conditions. And natural gas is an evident choice. Most people probably know about the advantages of natural gas for emissions. So just a reminder, greenhouse gas emissions, you have about 25% reductions for the same electrical production. And also not to be neglected, it's not the point of this conference, but NOx reductions are really high. And as surprising as it can be, we're really in the middle of nowhere. As remote as we are, we do have smog problems, so NOx problems. So this is actually a great advantage with natural gas. One thing I want to say though, to finish on this technical detail, is just to say that you do have to think about certain things if you use natural gas. One of the main things is depending on the engine type that you have, so depending on how fast it is, the speed, the size of the engine, it may be much slower to react, so you may have network stability problems. So whenever we go into the natural gas, design has to be taken into consideration for the power plant, but also the rest of the network, so even the process plant equipment. So this is quite important to be thought of. Now, this is where it gets interesting. If we talk about economics of natural gas for a site like Meliadine, we've talked with natural gas suppliers, we've done studies, and I was very surprised to see that the actual cost of the natural gas, once in its vapor form at the power plant door, is 5 times more than the cost of the actual molecule, so the feed gas that you would get here. So 5 times more, mainly because of the storage that we need in Rankin Inlet. We have to have storage for 9 months, 10 months, so it's huge storage for LNG, so you can imagine how expensive it is. And that accounts for 1/3 of the cost of our natural gas once delivered. Other important points are just the fact that you have to liquefy it, you have to transport it by sea, I was saying all around Quebec and all that stuff. And also just the fact that it's in a liquefied form, you got to bring it back to vapor. That takes a lot of energy, so again, that is costly. So 5 times more for gas than what you would pay in a pipeline down here. Now, taking this into consideration, and that's the interesting part, comparing it with the cost of diesel. Predicting cost of diesel is a science in itself, but as you can see, if you compare with the higher price or the lower price of diesel, the profitability of using natural gas in Meliadine is not that evident. As you can see in the slide behind us, the dotted lines are the high and low predictions, and natural gas can actually cost more for us in Meliadine than it would for diesel. But if you do take the average and be optimistic, we're expecting in the future years for natural gas in Meliadine to be about 10 to 20 cents less than diesel per liter of diesel equivalent in terms of energy. So there will be a certain difference. What I haven't talked about is this is just for the cost of natural gas. So if we add a carbon tax in there, that will have an impact, but the impact is not that large. So we're talking about 2 to 3 cents more per liter cost difference for natural gas. Now, that being said, with this situation, with the possibility of having natural gas, what are our options in terms of generation? So there are dual fuel engines that are now available on the market. There's more and more coming up for power generation. It's an interesting option because you can switch from diesel to natural gas very quickly, very instantly. But right now where we're at is that the cost of these dual fuel genset is actually 10 to 30% more of the cost of a standard diesel engine. More than that, dual fuel engine, when it works on diesel, is actually 2 to 3% less efficient than a 100% diesel engine. So for a case like Meliadine, with the electrical load that we have, we'll actually be consuming 1 million liters more of diesel with a dual fuel engine than we would with a standard engine. Sorry, just take a bit of water. So, so while we're waiting for natural gas, if it ever happens, if it becomes interesting and everything, we're actually consuming 1 million liters more of diesel. So this was definitely not an interesting option for Meliadine. Throughout our discussions with the suppliers, we found that there was another option, and that another interesting option, and that is to actually buy a genset that's on diesel, but that you can later convert to dual fuel. So the engine is pre-designed for future conversion, but at day zero, it's as efficient as a 100% diesel engine. And what's really interesting is it actually only costs 1% more than the standard diesel engine. So pretty much a no-brainer on that part. When you want to convert it, it's it's 15% of the original cost of the genset, and the main advantage is it only takes 2 weeks to convert. So this really gives you a lot of flexibility. You have a power plant that's as efficient as 100% diesel, but you can convert whenever it seems interesting with economics. As other information also, heat recovery, all the other systems stay exactly the same, so you're really just doing modification on the engines, but the rest of the power plant stays pretty much the same. We chose an option with a supplier that we felt was presented little risks. That is because the way it is pre-designed, you don't have to do any machining on site. Everything has blind flanges, bolts, everything, so very easy to do on site, and no major changes in major parts. So, for example, the cylinder diameter is exactly the right diameter for natural gas. So everything is quite simple. I'm getting quite technical right now, so I'll stop. But if you want more details, you can come see us at the booth, and it'll be my pleasure to talk more about it. Briefly touched on the power plant side. So this was a genset. If you do want to do a conversion, you plan it in advance. You can plan your ventilation systems to be good for both engines. So no extra cost there. One very important thing is that there won't be additional classification to be done. So it won't be considered as a hazardous area if you plan it in the right way, meaning that all electrical systems, all instrumentation, nothing has to be explosion proof. So you're really just working on the actual engine. And you can plan, we've planned other stuff. We've put flanges, blind flanges on the exhaust system for future ruptures. Yes, we've kept some space in the pipe racks for the natural gas piping, and under the genset for the module, natural gas module. So my point is more to say that these are all small things that you have to plan and design, but that don't necessarily cost much more. So you're actually pretty much paying only 1% for that genset that will be converted, and you're keeping a lot of options open when or if you do want to change. So all that being said, where does that put us in terms of economics, of profitability? If we took a standard option, which is a good option with an efficient engine, over the 14 years, we estimate the net present value, the total net present value of power generation, to be around $500 million for those 14 years. Now, assuming that we'll get natural gas in 2 years, that will be at the cost that we have predicted, this would give us $28 million of savings over those 14 years. So it's very interesting. Even though it cost us almost less at first, we're open to these pretty high savings if ever the cost of natural gas would allow. And carbon tax, we have to talk about carbon tax. Well, just a $30 carbon tax will actually bring those savings up to $35 million for the 14 years of power generation. So this is very interesting. And I'll maybe just finish by talking about greenhouse gas emissions. So when natural gas will be available, then we'll be saving or reducing our greenhouse gas emissions by 25,000 tons per year. Very easy solution, but with pretty good results. So I've talked about the fact that power plant, we wanted to design to keep all the options open. The fact that it was a very low capex that we're building up to a full solution after in terms of ore processing in power plant also. I've touched on the natural gas part of it, but we've done many other things. We won't go into the details, but maybe I'll let Danielle just talk about these 3 points, 3 additional things that we have planned or that we've done on our power plant that we find very interesting and that is easily doable for any off-grid power plant.
Thanks, Nick. So really what we've tried to do with our project, and Nick mentioned it, is we've tried to keep our option open. I think paying 1% more on the capex to have the opportunity, and you've presented the number, Nick, it was an easy decision. Now I think that most of the time we're looking for the, let's say, slam dunk solution. We're looking for the big project that will save a lot of money. In Meliadine, we did a smaller thing that will also have an impact. So every megawatt of heat produced by our power plant will be used somewhere else on site. So one item, the heat recovery system, we're going to heat the underground mine. There was a plus value to bring a 2 kilometers water line to this system to heat, pre the air, instead of burning fuel there. So I think the number is 4 million liters of fuel that we're going to save by doing that on a yearly basis. So smaller item, summer diesel, it's just in the design of our tank. We have to manage it a way that we do not mix winter fuel and summer fuel, but there again, 2 to 4% saving in efficiency using summer fuel when we can use it. So smaller things that could help the efficiency of the site. Last slide. Again, I think the message is that it's important to keep the option open at the design phase. You know how mining projects are, low capex, the schedule is tight, but we have to play around this. So the numbers speak for themselves. If we move forward with the LNG, 35 million in saving, 25,000 tons per year of GHG. So really, I think that keeping the option open is important. So thank you, everyone.
Thank you.